No.
Every time you take a derivative, P.S., we started off class today taking a derivative, you can make a corresponding integral formula. So in homework, I do believe somewhere at least, they have you take a derivative and then show a corresponding integration formula. Basically, absolutely every derivative we took last semester, we could make integration formulas out of.
Nice.
If we wanted to. Now, then we'd have to memorize them all, so we're not going to do that because that's going to be really tedious and annoying. We looked up on Amazon, I don't remember if it was in period 1 or period 6, was it you guys? The book of integration tables, maybe it was even CalcAB. But it has like 1,100 something pages, and those are ones that engineers and stuff use in like higher math courses. It's called integration tables. Yeah, there are formulas upon formulas upon formulas that you could access and you could use. Now think about it. They would have to categorize them in order to be able to have someone even find the right one. But the struggle is derivatives can, or do, get simplified down so much, sometimes it can be really hard to go backwards. So even though we could make an integration rule, we're not going to memorize every single possible integral out there. And remember, I said on Friday, and I think Thursday too, there is no quotient rule backwards, because every quotient rule, there's all sorts of stuff that like cancels and simplifies and multiplies and sometimes reduces. So it can be really hard to look at the answer and know exactly where it came from. So we're not going to be memorizing, even though the book has you find an integration formula. That's ultimately what this is kind of having us do. Take a derivative and then make a corresponding integration formula. We could make all kinds, but the nice thing is we're not going to have to memorize all of them. So even though that forever card is a little bit messy with all the different rules, be thankful that we're not having to memorize absolutely all 1,140 something pages of rules. But number 6 is one that we should recognize. We won't necessarily recognize this fact, but we should recognize him and say, but wait a minute, he's much more basic than that guy. How can I rewrite, even though he's nasty, a cube root of x squared? X to the 2/3. And all of a sudden, I have a basic rule of integration that I can use. And what rule is that? Power rule. Good, Adam. So someone else fill in, because Adam probably has it in his head right now. What is the power rule? The integral of an x to the n dx should end up leading us where?
X.
What's the power of?
N
Plus 1. So I need to go backwards at power
n
rule.
plus 1.
But when I derive, that power comes down. I need it to reduce. So over n plus 1, all plus c. And we notice when there are fractions, that whole 1 over guy is going to end up making a reciprocal. Maybe we can use that here. Because if we try to add 1, I wouldn't add 1. I would add
3/3.
3/3 to make my life a lot easier. And if I have to divide by, well, it's kind of messy, right? If I have to divide by that whole addition, technically, this is how the rule would have us do it. But have any of you realized in your practicing that it's going to be a lot easier to just figure out what this is? It's x to the what?
5/3.
5/3. And then instead of thinking about 1 over 5/3, just think about multiplying by
Reciprocal.
the reciprocal. And how can you check any integration antiderivative answer? Derive it. And if I bring down 5/3, isn't that going to reduce with 3/5 by the, it's not inverse. Multiplicative inverse property? What do you call that? A over b times b over a is always 1. I don't know, something way back when. Is it multiplicative inverse? I don't know. But if you bring down 5/3, 3/5 will reduce. You subtract 1, subtract 3 over 3, and I end up with my 2/3, which is the cube root of x squared. Okay, so those basic rules are going to help us to do a lot. Maybe not everything, but a lot. And the everything these won't be asked of us unless they have us do something weird in homework, like take a derivative. Guess what? It could be a rule, and you say, thank goodness I don't have to memorize. Okay, I said we're going to do just a couple like logistically things. That whole plus c thing that we already talked about, I kind of saved this till right now because I wanted us to practice as much as possible on Friday. But a couple logistical things. That whole plus c, sometimes I'll call it the arbitrary constant More often than not, I'll call it the constant of integration. When anti-deriving, when taking an integral, this plus c, we've already talked about how the derivative of any constant is 0, so therefore we have to have this plus c to allow for the possibility of there being a constant before the derivative was taken or in the antiderivative. However, up here, as soon as we have this plus c, now this one antiderivative became a whole family of antiderivatives. That's a technical way of talking about it. It's not just one antiderivative. I mean, it is one capital F of x, however, the plus c kind of makes a whole family. And then we have this new term. I mean, the organic chemistry tutor, used it in his video. I've used it a few times, but this whole phrase of indefinite integral, just kind of telling you guys what that is. An indefinite integral is an integral without bounds. You saw in the video how sometimes there are going to be bounds, like a beginning to an ending, a starting to a final. We're not there yet. I just want you to know, if you hear indefinite integral, that means, number one, we don't really have this plus c, at least not without more information. And number two, we don't have a lower limit, or upper limit is what we would call it, of the integral. Graphically, if we were talking about a family of antiderivatives, for instance, if we were to do something like the integral of 3x squared dx that we've already talked about in the past being x cubed plus c. So if we were to talk about that integral, technically we would say that this antiderivative is a whole family. And the reason it's a whole family is because technically, if c is 0, or if c is 1, or if c is 2, or if c is 3, or if c is -1, or if c is -2, pretend that those are actually somewhat the same shape, because now I'm starting to make them all kind of loopy-loop. Anyway, it's starting to get weird. But the idea is that there's infinitely many different possibilities, except or unless. Unless they give us some particular clue. Because if they give us some sort of what we would call initial condition, some sort of point that actually has to be on the curve, well, guys, if they say something like 0, 0, 3 has to be on the curve, all of a sudden I go from having infinitely many possible solutions, I go from an arbitrary constant to being like, nope, it's a particular solution. If I'm given a clue, if I'm given an initial condition, if I'm given a point, all of a sudden it's not supposed to stay general or ambiguous. Now all of a sudden I've gotten to one particular solution. We'll talk more about that, but anyway. There is a whole family. The plus c stays just a plus c unless they give us a clue, unless they give us a point. And we call that point an initial condition. Sometimes it's when x equals 0, but technically it could be any point. It could be, I don't know, like 1, 7. Only one of these curves will go through 1, 7. So down here in the notes, ooh, that's lopsided. Sorry. Down here in the notes, it says you can only find c when given a point. That's what I showed up above. You can only know what c is as an actual number if they give you some sort of point up above. Let me go ahead and make this bold and make it blue. Maybe that'll help it stick out a little bit to connect it. And then the other note is that derivatives and integrals are inverses of each other, which hopefully we kind of know because integration is undoing the derivative, antiderivative, and undo in math is always an inverse relationship. So I'm going to write off to the side. Just a quick reminder. Remember, they undo each other. And so the idea is if we take the integral of a function little f, which is also capital F's prime by the definition of antiderivative, the integral would be that capital F, that antiderivative plus c. And if I take that derivative, I get right back to where I started. The c disappears, and the derivative of f is right back to capital F prime. So you can see taking an integral, then taking a derivative, you end right back where you started. That shows that inverse relationship. And there's one more concept-y page, but I think it's even shorter if I can get there. Oh, we already talked about it. Sorry, I just introduced it earlier. How do you find C? Initial conditions and particular solutions. I already used that terminology over there. So just giving you the name for the C can solve for the, oh man, I already wrote all of it. Constant of integration, aka the plus C, when given a particular point. It's called an initial condition, but it doesn't always have to be at x equals 0. Given a particular point, given any point of the original function. So like that word problem. Remember in the video where he did a word problem from amount to rate and then from rate to amount? One needed a derivative, the other one needed an integral. And that one, I think the organic chemistry tutor guy was talking about the amount of water in a something. Where was the water flowing? I don't know. There was water in like a tank or something. In that one, it talked about in the second problem, it talked about like how many gallons were in the tank at the beginning. That's an initial condition. But in that one, they weren't asking for the function of how much. They were asking for the change, how much water flowed between this time and this time. I think it was 20 to 100 or something like that. So it was a little bit different in that it was just asking for the change in the water. That's a definite integral from like an A to a B. But anyway, long story short, they could give you in an integration word problem a rate function asking you for the function of the original, but for you to give the actual function with the plus C being known, they have to give you some sort of clue, some sort of original how much amount at time and how much was there. Otherwise, all you can say is how it's changing. You can't say how much is actually present. So, if we have a derivative, we can also remember, call that in context of a word problem, a rate function. If we have a derivative or a rate function, and if we have a clue, if they ever say solve the initial value problem, what they mean is, okay, you know how much y was present when x equals 1. It was 0. If they're asking you to solve the initial value problem, they're asking you to solve for y equals f of x. And how do we get to a y equation given his derivative? How do we get to him with him? Integrate. Good. So we're going to go ahead, and if you want to be super snazzy, technically we would go ahead and move this guy, separate those differentials. We'll learn more about this, don't worry. But we'll separate those differentials. Technically, we would take the integral of both sides. Remember, these little dy, dx's are little bookends. You have the integration sign on one side. You have the differential on the other side. What's in between is the guy you're supposed to antiderive, is your integrand. So this guy's in between is a 1, whose integral would just be a y plus c, but we will move that plus c over here. But the weird thing is, I don't think I want to keep this guy written as he is. I think I want to rewrite him. So I'm not integrating, I'm just rewriting. But why am I pulling a 1/8 out, guys, and rewriting with a 1 over x cubed? What did I just do?
You distributed the cubes.
Yeah. So 2x, 2x, 2x would be 8x cubed, and isn't 1/8 just a constant that I can pull out?
Yep.
And then, wait a minute, I don't think I want to leave him like that either. I think I want to make this 1/8 integral of x to the -3, so I can use my power rule. And then I can go ahead and add 1 to that -3, which would make -2, divide by the -2, so that when it comes down, it would reduce. If I was taking a derivative, that 1/8 is just chilling. So I'm doing great. It just looks kind of gross because I need to do a multiplication, and I have my plus c. So let's move this guy up because right now he's kind of getting a little lopsided. Let's move our constant of integration down, which is great. So I could make this -1/16 squared in that denominator?
Because make positive.
But why am I not done? But good.
Because we have y or constant.
Because I have a clue, and with clues, I don't stop. I need to go figure out who C is. Sure, that works. So I'm going to plug in the point when x is 1. Remember, f of x, y of x. It's a similar notation. X is 1, y is 0. So I'm going to go ahead and plug in check. So y is 0 when x is 1. PEMDAS would tell me to do exponents first, right?
Yep.
1. Then multiplication, 16. So negative 1/16 plus c is 0. Isn't c positive 1/16 when you solve? So what is my final solution? Y is equal to negative 1/16 1 over x squared minus 1. Ooh, I was messy. Technically it'd be negative 1 over 16 x squared plus 1 over 16. But the AP loves to say, ooh, fractions, ew, gross, let's get that out of there. So anyway, this one could be, or making it match, this one could be, if it was a long answer. Well, leave it as unsimplified as possible. But do you guys see how there won't always be a plus C? I mean, there will be to begin with, but sometimes you need to plug in and solve, because even though there's a whole, infinite family of possible antiderivatives, if they give us a clue, they've established what we call a particular solution. Cool? So to that end, we're not going to get out whiteboards and all that stuff today. We might actually start class back tomorrow. But I do want to see what you guys are able to do. But I want you to kind of have some of the pressure taken off, because most of you hopefully try to keep your notes really nice and neat and organized, right? And you want everything in your notes to be perfect. You can study it for a test and all that jazz. Can you just flip to the back of your homework star? Let's just go to our workspace. We're going to spend 5 minutes just playing with integrals. You, yourself, and you. No group collaboration, no one like speaking over your shoulder or telling you what to do to get the answer fast, and you have no clue what you're actually writing, you're just being obedient. None of that. Just you, yourself, and you competing against yourself. Go as slow or as fast as you want. I'll be doing it on a whiteboard, so if you're ready to check your answer, I'm going to throw a few up on the screen. If you're ready to check your answer, you can go ahead and let me know. I'll come show you the answer. You get it right or you get it wrong, and you move on. Sound good?
Sure. You just knocked the strawberries too. Nice. Okay.
Let's go here. We have a few other like homework type problem-ish examples. Let me see if there's any like clues or hints I want to give you for homework. Slope. If you still have your notes close, you might want to say, let me dual page this just for a second. These aren't the ones I want you guys to like prove your worth on right now. Don't stress. I'm just going to throw a few hints in here at the end of the video for the homework. If you see something like this, would you guys please think of foiling, right? Rewriting with foiling first. Do we see that? There is no chain rule or product rule for integration, so we'd actually have to FOIL it. Rewrite it by foiling, and then take the antiderivative piece by piece. If you see words in homework, are you going to freak out?
Yeah.
I hope not. I hope you'll see something like slope equals and be like, oh, so dy dx equals? And can't we make a formula? And then once we see something like this, couldn't this be an initial? And so couldn't we just be integrating whatever the clues tell us to go backwards? Trying to get to y equals. And then here's one that you guys have absolutely no rule for. You don't have a rule for tangent squared. You don't have a rule for cotangent squared. But you do have these nasty, maybe not nasty, review Pythagorean properties that say I can change cotangent squared to actually just rewrite it.
Cosine over sine.
Ah, yes, but that even gets worse, or it gets even worse. The one you want to use is the Pythagorean that says that this will be cosecant squared minus 1.
That one too.
And guess what? He has an antiderivative, and he has an antiderivative. This one is impossible, but with one quick little trig substitution becomes possible. What? Secant squared minus 1. What? Adam saw tangent squared in homework? Oh my goodness. Okay. What? Secant squared minus 1. Okay, here we go. I'm going to give you a few. You guys try, and if you want to see the answer to one, just let me know. See if you guys can do all three.
This is something.
I have to check your answers one by one. Tomorrow we'll do integration competition with your groups. You guys will answer the
Collaboration.
Today, can you do it by yourself? Then let's check an answer. We have some ready. Don't have to have them all done. Get the first one done. You got it right. Anybody else want to check the first? Getting it? The first one? Add one.
This one's a little trickier.
Yeah, you have to memorize those rules, huh? If you're like, I don't have them memorized, okay, just skip number 2 and go to number 3. If you don't have them memorized, okay, you don't memorize them, skip number 2 and go to 3. It's just the words of the wise as you're doing homework.
Huh.
If you haven't checked the first one yet, you can look up at the front because I wrote down 2 different ways that were both totally appropriate for number 1. Number 2, if you don't have the rules memorized, that's okay, as you do them tonight. Be thinking about, as you're looking at trig, getting them down. Number 2. Because we're asking ourselves who's doing it. Who's cosecant? Cosecant.
So number 3. So then you combine them all.
As number 3, we would rewrite to be x to the 1 times x to the 1/3, which is x to the 3/3.
And then you do the power rule together.
And then power rule would add 3/3 and multiply by the reciprocal. But some of you might have needed to see that. Kiddos, we are done for today. It is chapel, and I do believe the pretend bell has rung. But do some of you guys need to practice some more tonight?
Absolutely.
Yes. Are there going to be a few concept-ish ones? Do your best in the concept-ish ones. If you get stuck, bring them as questions. But there are going to be some good old-fashioned, can you rewrite and integrate using those rules and be memorizing those rules. Get out of here when you guys are ready. Oh, yeah, I was thinking, like, okay, horrible. At this point, you want to do it now rather than later. Bye, guys.
All right, Misty. See you later.
Later, Peter. Oh, yeah.
The packet is due today, right?
Bearings.
Because I lost my packet and so I did it on my